take care of talking about Hooke's law. Hooke's law looks like this. F is equal to a negative kx. And this is a vector. And this is a vector. And F, if we put a spring out here, and let's just talk about a spring right now since we're going to use this. Let's say we have ourselves a cup on a spring. It's similar to what we have inside of our mini launcher. Let's say that this is at equilibrium. So at this point, it's 0. So there's no pulling, there's no pushing or anything like that. If we were to compress this spring, we're going to have some delta x here, or some compression length. Let's just call it x. Okay? So since we have some x here, I want to take that as a vector, but since we have some x here, we are going to have a force acting back on you. At equilibrium, x is 0. So that means that there's no force. But when you compress it, you actually get this. All right. And now the K is actually, it's a property of the spring. It has to do with the stiffness. So I'll just say stiffness. And this is going to be compression or extension. Okay? So now when you compress a spring, you see how you have this negative sign? We know that it's going back, so that's a negative sign. The ultimate force is going to be positive. So it's going to come out like so. So this is going to be our force. All right? That's pretty much the analysis right there. We have our force here, and we have our stiffness. Okay? So that's the analysis in terms of the force. This is Hooke's law, and I feel as though I should write that on here. Hooke's law. Now let's look at Hooke's law in terms of energy, okay? So we want to relate Hooke's law, the compression length, to velocity. So the way we're going to do that is by using the conservation of energy. So let's look at this. You have a scenario where you have a spring, it's compressed, and you have a certain amount of energy that's stored in that compressed spring. This is called potential energy as well. And I'm just going to call that potential energy, let me not call it K. Let's call it H for Hooke's. And this is 1/2 kx squared. That's the potential energy for Hooke's law. It's the energy stored in the spring. So when the spring is released by the trigger, then we are going to get something else. So if our ball is located right here, it's located right here, then, hold on for 1 second. What's going on? Yes, Brad. We can turn those lights on. So if we have our spring here, it's going to have a certain amount of potential energy in it. And once the ball is released, it's going to move to a different location. And let's choose a location where the ball is no longer in contact with the spring, and it's just going to have pure kinetic energy. So we know what kinetic energy is. We've already worked with that. That's 1/2 mass times the velocity squared of the ball.